Thank you. All right, so I wasn't, I was debating for a long time what to speak about, and decided I'll do this something which is really algebraic geometry, but it is about trying to understand mirror symmetry for hyperkähler manifolds and in particular for these integrable systems that arise from moduli of flat bundles. And the advantage one has there is that the geometry is extremely rich, and also it's related to the geometric Langlands correspondence, where we have extra symmetries which can guide you in the construction of the mirror correspondence. So I want to sell this to you as some kind of formalism that allows you to understand the mirror correspondence, which we really understand algebraically as a T-duality or a Fourier-Mukai transform along the fibers of an abelian fibration. But then, in mirror symmetry, we're supposed to do a hyperkähler rotation kind of process. And the non-abelian Hodge theory approach to this geometric Langlands correspondence somehow packages these two things together and gives you an answer. And in fact, you have to work hard to get the answer. But it has exactly the features that you see when you struggle to describe objects in the Fukaya category on the nose rather than describe them as disquantization of large volume objects. So, okay, so hopefully I'll get the message through, but I'm not quite sure. So the starting point, somehow the background of all this, the real thing I really want to do is an example, which is going to take quite some time. But the background is this idea, which is maybe slightly naive, but still concrete, of how to construct automorphic D-modules on the moduli of bundles by using the non-abelian Hodge theorem. So the background is the non-abelian Hodge approach to constructing Hecke eigensheaves. And so
I'm bearing in mind that this is a background that I don't understand, but it means you're going to provide that.
Yes. That's why I'm talking about it. Yeah, so I'm going to do the most basic setup without any white noise that you have to worry about all the time. So I'm going to talk about the geometric Langlands conjecture for GL and C in its most primitive form, without any of the subtleties that you really have to deal with. So here we have say a compact curve And in fact, you'll see in my example, because I want to take the least complicated topological example that still has all the interesting features, it's actually going to be an orbicurve. But that's going to come in a moment. So say we have a smooth compact curve. And this geometric Langlands conjecture, it says that, again, in its most primitive form, that if we give ourselves a flat bundle of rank n, then we should get an irreducible D-module, I'm going to call it C sub V, on the, say, the moduli space of rank n bundles on C, and the on the moduli bundles with eigenvalue V. So such that CV is a Hecke eigensheaf with eigenvalue V. Yes.
So this means, I mean, there's a Hecke correspondence.
Yeah, I'm going to say.
Of the curve, and if
Yes.
you go along the curve,
Yeah.
it will tensorate with V.
Yes. So let me just say what this means. So this means the following. So for every I, say between 0 and n minus 1, you can do it, for arbitrary integer, but then they keep repeating. We have a Hecke correspondence Hecke I that goes from the stack of bundles to the stack of bundles. So it depends on a point of the curve. So if you put all of them together, it's really a correspondence from the stack of bundles to the stack of bundles cross the curve. And this Hecke guy is really the moduli of triples V, V prime, and a map from V to V prime with the property that so V and V prime are rank n bundles. Beta is an injective map of locally free sheaves. And the co-kernel of beta is a sheaf supported on a single point. And it has length I. So these are just pairs of bundles that are bimeromorphic to each other, and the difference between them occurs exactly at one point. And if you look at the map between the fibers has corank I. And the two projections are obvious. You map to V or you map to V prime times the point. So, no, yeah, I mean, I mean schematic support, but yeah, this is the scheme theoretic support. But in my case, it's always going to be the same as the set theoretic support. So
the co-kernel is a direct sum of I pieces?
No, the co-kernel, yeah, so what you have is V goes to V prime, and this is just a skyscraper sheaf supported at the point. Skyscraper sheaf supported scheme theoretically at the point, so it's just a vector space.
Yes.
And that vector space has dimension I.
It's a direct sum of I pieces.
Oh, it's a vector space.
Yeah. I mean, as opposed to the fat point.
Yeah, as opposed to the fat point, yeah.
It's not the fat
Yeah, no, it's not the fat point in this particular case. Yeah. So you have Ix lower star of some vector space of dimension I. And yeah, and then these Hecke guys, so they give an operator, let's call it Ti, that sends D-modules, or say the derived category of quasi-coherent D-modules on bund, to the derived category of quasi-coherent D-modules on bund cross C. By just pulling and pushing, well, in principle, you have to twist by the intersection cohomology complex on this guy, but since I'm doing GLN, these guys happen to be smooth. So You don't twist by anything, so you're just pulling and pushing. So these are just Qi, lower star or lower shriek, doesn't matter in this case. It's up to shift, composed with Pi, upper star. And, or if you fix a point, it's going to be for each point, but I'm not going to fix the point. And then the Hecke eigenshift condition is that if you apply these operators to the D-module CV, you're supposed to get back the D-module CV on Bun tensored with the pullback of some flat bundle associated with V by a representation, and these guys correspond to the fundamental weights of GON, so it's really wedge I of V. So this is for OI. And so what does this have to do with mirror symmetry? The point is that this is really secretly mirror symmetry for the integrable system corresponding to the moduli of flat bundles. So if we take log n to be the moduli of flat rank n bundles, this assignment, so V is a pointing here, flat bundles. Yeah, so there is a whole hidden issue here, which is that there is got to be a there is the character variety algebraic structure on the moduli of flat bundles, which is different, and then there is something on this side that corresponds to the modules on the character variety. So there is this Betty version of the geometric Langlands correspondence, which looks slightly differently, and they're both clearly related to mirror symmetry. And in fact, the Betty version seems to be better adapted to mirror symmetry. Yeah.
Tensorization is.
Yeah.
I think he means at the point of log n, which is the point V, in this case tensor by V. Is that what you?
I mean,
There's an operation.
no, it's an autoequivalence of the category.
Yeah. Which at each point is tensor by V.
So the point is that on the local systems across the curve, we have a universal local system, right? And it has an underlying universal bundle. So it's really a universal bundle together with a relative connection. And the tensorization operator is an operator, so T, Wi. So it's going to be again a map from the derived category of all modules on the local systems to the derived category of all modules on the local systems cross the curve. Yeah, and Wi is just going to take whatever sheaf we have here, pull it back by the first projection, and tensor it by the ith exterior power of V. And the claim is that this is a commutative algebra. Well, if you fix the point, it will be a commutative algebra for all points, which is isomorphic to the Hecke algebra. And this equivalence is supposed to intertwine the two operations. And I still haven't gotten to the mirror symmetry. Yeah, no. The Pierre's question was, what happens here if we change the algebraic structure?
Yes.
Right. So instead of the flat bundles, you can take the moduli space of representations of the fundamental group, which has a different algebraic structure. It's analytically the same, but the algebraic structure is different. So the category of all modules is different. It's really different because, for example, this category of all modules reconstructs the curve, Whereas if you take the character variety algebraic structure in the category of homodules, it does not reconstruct the curve. It's the same for all curves.
Yes.
And so what do you put on this side? And there is an answer which is complicated. And so there is a Bethe version of the geometric Langlands correspondence, so there was a paper last year, maybe 2 years ago, by Ben Zvi and Nadler called Bethe geometric Langlands, where they worked out the geometric Satake correspondence and the geometric Langlands program in the Bethe context, and in fact checked it in several interesting cases. And that one seems to be actually really well adapted to mirror symmetry. Because mirror symmetry is, it's very strange. It's not really sensitive to the algebraic structure. It's sensitive to analytic, to complex structures, but not really to the algebraic structure. And so there are different varieties with two different algebraic structures that have the same special Lagrangian torus vibration for a given symplectic form. And so when you do the mirror, you get two different mirrors in the algebraic for the two different algebraic structures. So and the ones that we are used to seeing seem to be the one that correspond to the character variety algebraic structure rather than the flat one. So there is a lot to be said there and analyzed, but I want to stick with this one because this is the one that the projective geometry really sees most easily. So what did I want to say? Yeah. So this guy C is supposed to intertwine WIs and TIs. And why is that mirror symmetry? The reason this is mirror symmetry is that, of course, so the heuristic remark which I'm going to elaborate on is that this category of D-modules on Bun N can be viewed as a quantization of the category as a quantization of the category of O modules on the cotangent bundle of Bun N. And the cotangent bundle of Bun N, which is the moduli of Higgs bundles, well, at least if you ignore stability and you work with the stacks, so the cotangent bundle of Bun N, if you work with the stack and ignore stability, this is isomorphic to so isomorphic in quotes to the moduli of Higgs bundles of rank n. So these are coherent sheaves, vector bundles of rank n, and all linear maps from E to E tensor the canonical class, which square to 0 in this case. This is automatic because we are on the curve. Given by the Hitchin map. Now you have two quantum objects that you can associate to the fibers of this Lagrangian torus vibration, or in fact to any Lagrangian in this Lagrangian in this homomorphic symplectic manifold. So for each fiber, let's say H inverse of B, say smooth. So that's going to be some abelian variety, which happens to be a Jacobian of spectral curve. We'll come to that in a moment. So this fiber, we can look at two associated quantum type of objects. One is an object in the Fukaya category supported, whose class is that Lagrangian, is the class of that Lagrangian, is supported on this fiber. And the other is yeah, so this thing you can say is some kind of a quantization of the structure sheaf of that Lagrange. Right? I mean, in the large volume limit, it will be just a flat rank 1 bundle on the Lagrangian, and then you need to quantize to get an object in the Fukaya category. So it's some kind of quantization of the structure sheaf of the Lagrangian. And then there is another object that you can construct that is you take the structure sheaf of that Lagrangian, think about it as an element in this category, and then quantize it to a D-module. So a D-module on Bun, again, which quantizes or micro-locally quantizes. And of course, you have to say how that happens. But there are somehow two potential ways to deform this object, which is the structure sheaf of a Lagrangian torus. One is as an object in the Fukaya category. The other is as a D-module, as a sheaf on the cotangent bundle. And this equivalence, now you can, from this point of view, if you believe that these two quantization procedures are somehow related to each other, that they're the same, then you can think about this as some incarnation of the Fukaya category of the cotangent of the moduli of Higgs bundles. And the point is that the moduli of flat bundles and the moduli of Higgs bundles are hyperkähler rotations of each other. They're in the same twistor family. They're two fibers of the same twistor family. So what this is supposed to say, it's supposed to say that the derived category of all modules on the moduli of flat bundles is the same as the Fukaya category of the moduli of Higgs bundles, which is homological mirror symmetry. The great advantage of viewing it this way is that you have these extra symmetries, the Hecke symmetries, which give you a lot of information of what this thing should be. So if you want to understand, so a priori what you want to say is that this thing is supposed to be some kind of dualization along the fibers of the Hitchin map, composed with hyperkähler rotation. And you can try to say that, so the idea or the program is interpret C as Fourier Mukai conjugated by two non-abelian Hodge correspondences. So let me try to explain that. So the non-abelian Hodge correspondence, so the Corlett-Simpson theorem it says that if you have, say, a smooth polarized projective variety, then there is some equivalence of categories which says that, okay, I'm going to say rank n flat bundles. I mean, it's really an equivalence of categories for all ranks with the tensor structure and the digi structure, but I'm not going to go into that. But it says that rank n flat bundles are actually equivalent to rank n Higgs bundles, which are semi-stable of degree 0. Well, in any dimension, it's going to be semi-stable of first and second chain class equal to 0. Semi-stable with respect to the given polarization. And so if you imagine, so if we can apply this to C and to Bun N, then if we could apply this to C and to Bun N, then we can try to describe the mirror symmetry or the Langlands correspondence in this case as a composition. You do Fourier Mukai along the Hitchin fibers. So this is a Fourier Mukai on Higgs n. To get to Higgs n, you have to apply the non-abelian Hodge correspondence to C. And then, so CV is supposed to be the non-abelian Hodge correspondence applied to the structure sheaf of the point, to V itself. So that will give you a Higgs bundle on C. Then you take the structure sheaf of that Higgs bundle, take the skyscraper sheaf of that Higgs bundle, apply the Fourier Mukai transform to that, and then you'll get a coherent sheaf on the moduli of Higgs bundles, which is really, because this is just a structure sheaf of a point, Fourier Mukai of a structure sheaf of a point on an abelian variety just gives you a line bundle on that abelian variety. So the answer, so the effect of this Fourier Mukai would be a line bundle on the corresponding Hitchin fiber. And then you can apply the non-abelian Hodge correspondence on Bun N.
But then the other one is not really a flat bundle.
Which other one?
So CV is not a flat bundle, so it's kind of extended.
That's right. So you mean it's a D-module? It's not really. Yeah. No. But so the that's why I say T. Right. Right. But so. Yeah, so maybe this one requires a little bit of an explanation because this object here is a coherent sheaf on the Higgs moduli space. And I'm saying I can apply the non-abelian Hodge correspondence to that. But the non-abelian Hodge correspondence applies to, this is the inverse non-abelian Hodge correspondence. Non-abelian Hodge correspondence applies to Higgs sheaf. But the point is that those think about the because we could think about the Higgs moduli space as being the kind of cotangent bundle to bund n. And so here we have this sheaf, which looks like a line bundle of degree 0 on a Hitching fiber. So this is the thing that I called all of the non-abelian Hodge correspondence applied to V. Fourier-Mukai of that. Right. I took a point in the Hitching fiber, which was the Higgs bundle corresponding to V, look at the skyscraper sheaf for that Higgs bundle, and then look at the Fourier-Mukai duo. It's going to be a degree 0 line bundle on the same Hitching fiber. So that was this guy. And so we took that. It sits inside. So it's a sheaf on a compact variety in the total space of a cotangent bundle. And you can think about it as a spectral sheaf. So the point is that this Hitching fiber sitting inside the cotangent bundle maps to the moduli of bundles. And this map is finite. Well, I'm cheating here a little bit, but finite. So once you have a line bundle, you can just push it down. So the push forward of F is going to be a coherent sheaf on bund n, in fact, a vector bundle on bund n, equipped with an action of the symmetric algebra of T. And that gives you a Higgs field. So this looks like a Higgs bundle on bund with some Higgs field. So Higgs sheaf or bundle on bund. So the point is that the Hitching fibers, you can think about them as spectral covers for the moduli of bundles. And line bundles on those spectral covers give you Higgs sheaf on the Higgs sheaves on the moduli of bundles. And then you can, if everything was working nicely, you could apply the non-abelian Hodge correspondence to that.
Okay, very slowly.
Yes.
Wait.
Okay. Maybe the notation is too cluttered. So okay, let me do that. So here is what we want to do is we want to start with V and produce CV, which is a D-module on bund n. Okay. So the first thing you do is you apply the non-abelian Hodge correspondence on C. So that gives you a Higgs bundle. Let's call it E phi. So this is in Higgs n. It's still a point.
Is it necessary for V to be irreducible? Or?
No. Any local system gives you a semi-stable Higgs bundle. This equivalence says, notice there is no stability condition, there is no irreducibility. It just says any local system gives you a Rankine Higgs bundle which is semi-stable with vanishing Chern classes. This, by the way, there is something about this. So once you start doing orbicurves or ramified situation, this is no longer true. There is a stability condition on this side as well. But I mean, in the way I'm formulating it, this is anything.
So we have it. Okay, now we have the Higgs bundle.
Okay, so you have a Higgs bundle. Now you take this Higgs bundle and you think about it as a skyscraper sheaf on the moduli of Higgs bundles. It's just the sheaf, the structure sheaf of that point. It's a coherent sheaf on Higgs n. Okay. Now you Fourier-Mukai this guy. So Higgs n is self-dual because we are doing GON. The fibers are principally polarized abelian varieties. So if you dualize the, you get the same moduli space. You have a Poincaré sheaf, and you can pull this guy, twist it by the Poincaré sheaf, and push it forward. So you Fourier.
This is the line bundle on the Hitching fiber.
Right. So this is so this Fourier-Mukai gives you what did I call it? F which is the line bundle on the Hitchin fiber.
So this is the fiber-wise original Fourier type.
Is the usual T-duality in algebraic geometry. Okay? Yeah, so this is the line bundle on Hitchin fiber, which is H inverse of H E phi. Okay. Now, you stare at this for a moment. This is a coherent sheaf on the cotangent bundle. So it's a line bundle on the Hitchin fiber. In particular, it's a coherent sheaf on the cotangent bundle of Bun N. And you realize that the Hitchin fiber maps, so it's inside the cotangent bundle of Bun N, and it maps finite to 1 to Bun N. So you can just push it forward. And when you push it forward, you get a coherent sheaf. And you also get an action of the cotangent bundle of Bun N because there is a tautological section on the total space of the cotangent bundle that you can multiply this guy by. And that gives you a module structure over the symmetric algebra of the, this is affine over Bun N. So it's just the spectrum of the symmetric algebra of T. So it gives you an action of the symmetric algebra of T. And that action is theta. So this gives you a Higgs sheaf on, so this is really an equivalence, a Higgs sheaf on Bun N. So Higgs of some unspecified rank, which I'm not going to talk about, on Bun N. And now, if you could apply the non-abelian Hodge correspondence to that Higgs sheaf, so if it's semi-stable with vanishing chunk classes and well, then you can just apply the non-abelian Hodge correspondence in the reverse on Bun N and get CD. Uh-huh. Mm-hmm.
What about that the X fiber are principal modulus in the abelian variety?
Yeah, so I suppress this whole thing. So there is an enhancement of all this. So if the modular space of Higgs bundles has connected components where the fibers are the homogeneous spaces over the abelian varieties, and those correspond to gerbs on this side. So you rather than getting a coherent sheaf on the modular of Higgs bundles, you get a coherent sheaf on a gerb over the modular of Higgs bundles. So if you do it with the stacky structure, then it all aligns. Just that the connected components on this side become the stacky guys on the other side.
I didn't understand the last.
But I suppress that completely.
What are we applying?
Yeah. So this is a Higgs bundle on the moduli of bundles. I interpreted the object in the Fukaya category as a Higgs bundle on the moduli of bundles. And now I can apply again the non-abelian Hodge correspondence in the reverse to get a local system, which will be a D-module. And as Misha was saying, this doesn't quite work because, of course, there is no chance for this CV to be smooth. But yeah, so let me say where this thing breaks. Yeah, yeah.
So you would apply the correspondence to the moduli space of bundles, and it would get you a flat bundle over the moduli space of bundles, which would be a particular case of
So D-module, yeah.
So the first time we applied this correspondence to the curve.
Yes.
The second time.
It's on the moduli of bundles. Yeah. And so there are two places where this program breaks. And it breaks in an essential way, so you need to tackle these problems. One is that the moduli of bundles is not a smooth projective variety. So even if you impose stability on the bundles, if you do them stable, then it will be smooth, but it will be quasi-projective. And if you do semi-stable, because they are degree 0 bundles, then it has singularities. There are singularities in very high codimension, but so you could, in principle, actually modify the non-abelian Hodge correspondence to work on these guys, and there are versions of the non-abelian Hodge correspondence that take singularities into high codimension into account, but they're ramified versions of the non-abelian Hodge correspondence. But you need to do something. I mean, you can't just use the non-abelian Hodge correspondence directly. So that's one place where it breaks. But it also breaks here. Even if you were willing to handle the singularities of the moduli of semi-stable bundles, it's not true that the cotangent bundle of the moduli of semi-stable bundles is isomorphic to the moduli of semi-stable Higgs bundles. So if you ignore stability, if you do the stacks, they're isomorphic. But if you impose stability, you look at the coarse moduli spaces, that's not true anymore. They are birationally isomorphic, but they're not isomorphic. And what this affects is it says that this spectral cover, this object of the Fukaya category, you really want it in the cotangent bundle in order to construct the Higgs field in order to run the non-abelian Hodge correspondence. So what you'll get is you'll get some open part in the spectral cover sitting in the non-abelian in the moduli of bundles. And in fact, it could happen that the spectral cover is not finite over the base, that it has positive dimensional fibers in some high codimension. And so this part of the construction and the non-abelian Hodge correspondence are then both under suspicion. And so you need to handle this. And the way to handle it, to understand that really there is no chance that on the moduli of bundles you can run the non-abelian Hodge correspondence in its vanilla form. You really need to do the ramified version of the non-abelian Hodge correspondence. Yeah, it's going to be a local system, but it's going to be a D-module that's generically smooth, but it's going to be a local system that has poles. And in fact, both irregular and regular singularities appear in the picture, but in the example, luckily, everything will be regular. So, and okay, so we need to fix the technical issues. And as I said, there are two technical issues. One is that bun n is singular. And the other is that the map from the spectral cover, from the Lagrangian inside the Higgs moduli space to the moduli of bundles is not a morphism. Is not proper entomorphism in general. And it's really worse than it not being a morphism. It fails to be a morphism in codimension 1. It fails to be a finite morphism in codimension 1. So let me give a name to this hitching fiber because I'm going to call it JB. So this is the Jacobian of the spectral curve. Given by B. Right, I didn't say what the hitching base is, but the hitching base is the sum of powers of the canonical bundle up to the rank. And so if you have a point B here, it has B1, B2, Bn coordinates, and then you get the spectral curve, which is y to the n plus B1 times y to the n minus 1 plus Bn times nothing equals 0. So this is a curve in the total space of the cotangent bundle of C. So this is this CB, and JB is its Jacobian. And so the claim is that if you take JB and you intersect it with the cotangent bundle of the stack of bundles. So the cotangent bundle of the stack of bundles is actually an open subset in the stack of Higgs bundles. Because if you have a bundle which is semi-stable as a bundle, every Higgs field on it will make it semi-stable as a Higgs field. So all those guys are inside. It's an open dense subset. So if you intersect it, then you get a morphism from this intersection, the projection to bund N. So this is an open inside JB. So this is this rational map. And the point is that this map is not proper. And it fails to be proper exactly over the wobbly locus. So it's quasi-finite, but not finite. So this fails to be finite over the wobbly locus. So bund N consists of semi-stable rank N vector bundles. Inside, of course, we have the interesting locus of bundles that are stable. But there is a slightly smaller open set, which consists of the bundles that are very stable. So these are the very stable vector bundles of Lumon. And these are defined to be vector bundles E such that the only nilpotent Higgs fields they allow are the 0. So for every phi, which is a Higgs field on E such that phi is nilpotent, this implies that phi has to be actually 0. So from the point of view of the Higgs moduli space, what this says is, it says that you have the fibers of the cotangent bundle. So the Higgs fields on a given vector bundle, this is just the fiber of the cotangent bundle. The nilpotent Higgs fields are a fiber of the Hitchin map, which is the 0 fiber, which is the nilpotent cone. A bundle is very stable if it has the property that the fiber of the cotangent bundle intersects the nilpotent cone at a single point. So these are two Lagrangian guys sitting inside the stack of Higgs bundles, or the moduli space of Higgs bundles, and you want them to intersect at a single point. That's the very stable condition. You can impose it on stable guys, but in fact, Lumon proves that this condition implies stability always. And so the wobbly bundles are the bundles that are very stable but not stable. Huh?
Stable, not very stable.
Stable but not very stable. Yeah. So a bundle is wobbly if E is in the stable locus but not in the very stable locus. So the point is that this condition with the transversality or the one point intersection with the nilpotent cone guarantees that this over every very stable bundle. And you can check that it's never proper over the wobbly locus. That you actually have points in the Higgs moduli space which are not in the cotangent bundle. And then you can study what the wobbly locus is, and the wobbly locus is a divisor. Well, semi-stable but not stable. So the wobbly locus in band N is a divisor. And in fact, conjecturally at least, so let's call it WOP. In all the examples that we've analyzed, is that this guy is normal crossing, and the Hitchin fibers, so and Higgs, and actually embeds in the total space of the logarithmic cotangent bundle of the wobbly locus. As an open set. So I don't really have good evidence for this conjecture, except that in the examples we can see that it happens. In fact, for the purposes of this construction of the duality and Hecke eigensheaves, because I didn't speak about the non-abelian Hodge theorem with ramifications, but the non-abelian Hodge theorem with ramifications is kind of powerful. So it allows you to have singularities in codimension 3, and it allows you things to be ramified. So you need things to be ramified along normal crossings divisors, but it allows you the divisors to be non-normal crossings in codimension 3. So what you really need to check that this is a normal crossing away from codimension 3, and that this happens away from codimension 3 in the base. But so what I want to say now is that away from this wobbly divisor, of course you can construct a Higgs bundle, but it's now a Higgs bundle on a quasi-projective variety. So an improvement of the program is to say that this Higgs bundle away from the wobbly locus, we can extend it naturally to a Higgs bundle with poles on the whole band N. So if I take the push forward of F, this really gives me this E. The map from the, so it gives me this E. So what you want to say is that, I didn't say this right. It's not true that the Higgs moduli space is a sub here, some blow up of the Higgs moduli space is a sub there. I mean, there is a map, there is a rational map from the moduli space of Higgs bundles to this guy, and you can close the graph of that map.
I'm a little confused. The hope now would be to construct some D-module on a stable bundle.
That's right. That's right.
Not on the stack of all.
No, the point is that you can, once you construct it on the stack of stable bundles, you can just do a middle perversity extension to, I mean, on the locus of stable bundles, you can do a middle perversity extension to the stack of bundles. And then there is a theorem. So you need to do everything so that it's compatible with all the operations. So there is a, so first you'll do some non-abelian Hodge correspondence and get a parabolic local system on the stack of stable bundles, on the space of stable bundles, and then do a middle perversity extension to get a D-module on the stack of all bundles. And you need to check that all the symmetries are compatible, but this Mizuki extension theorem for twistor D-modules actually guarantees that for the middle perversity extension. You still need to check that all the operations, all the Hecke operations and everything we do is compatible with the non-abelian Hodge correspondence, which I'm going to talk about maybe on Friday. But the part about the middle perversity extension is not a problem because Mizuki actually proved an equivalence of categories. But so the improvement will be that you take this guy, and this is now a meromorphic Higgs field on stable bund N, semi-stable bund N with the wobbly divisor, with parabolic structure. Along the wobbly divisor, so that the non-abelian Hodge correspondence applies. Yeah, so I didn't say anything about the ramified non-abelian Hodge correspondence. Let me say this now. Yeah, the point is that you get some meromorphic object, but you hope that you construct a meromorphic object to which you can apply the non-abelian Hodge correspondence. So, yeah, let me say what the Mizuki theorem says. So this is the tame non-abelian Hodge correspondence. And it's a theorem of Mizuki. What it says something very similar. So suppose that we have X, which is polarized, smooth projective, and D is a normal crossings divisor, and then it says that rank N parabolic logarithmic flat bundles on XD are identified with rank N parabolic logarithmic Higgs bundles. On X with vanishing first and second parabolic Chen class. And yes. And in this case, you have to put semi-stability on both sides. So there is a in the non-ramified case, the flat bundles are all semi-stable. The Higgs bundles could be semi-stable or not. In the ramified case, you have to put semi-stability on both sides. Yeah, so you can run this program as long as this guy has a logarithmic singularity, and there is an irregular version of this theorem, which is very complicated, and I'm not going to talk about it because it has Stokes data on both sides. And unfortunately, sometimes in this Langlands story, you do get irregular local systems. So you really need to worry about all of them. But at least in the examples that we've looked at, when you start with an unramified local system on the curve, the local systems that you get on the moduli of semi-stable bundles is with regular singularities. So at least in those examples, you can work with the regular case. So I'm only going to talk about the regular case. But yeah, so if you can apply, so if this guy with regular singularities that you get here has the property that it has some natural parabolic weights and a parabolic structure which makes it semi-stable, and for which the first and second parabolic Chern class are 0, then you can apply the theorem and get what you wanted. And then there is another theorem, as I said, of Mizuki, which says that if you start with a rank n parabolic logarithmic flat bundle and you restrict it to the open part where it's actually a flat bundle, and you do a middle perversity extension of that to any compactification, that actually gives you an equivalence between the categories of irreducible D-modules. So if you take, these are twistor D-modules which are irreducible, and you take all the irreducible D-modules of some compactification, and this is an equivalence of categories. Irreducible of a given rank.
Sorry, I'm confused again.
Uh-huh.
Your bund stable is not compact, so, but you are telling
Bund semi-stable. No, this is on bund semi-stable.
oh,
Bund semi-stable, yeah.
but then singular.
Yeah. The point is that this theorem, so I said that, but I didn't write it. I said this is not projective NC, but in fact, this theorem works if these two conditions are satisfied away from codimension 3. So in fact, that's how Mizuki proved it. And yeah, so now, so this is somehow the background. And now I want to really talk about the example. And I have 10 minutes, right? And then hopefully I'll finish it on Friday. Yeah, so we worked out, but so I didn't say what you really need to prove now. Okay, say that this all works. Say that you find some parabolic structure so that this gives you a local system. I mean, this is not enough, right? You want to make sure that on each stage the operations are compatible with the symmetries that we had, the tensorization or the Hecke symmetries, which means that on each stage, when you apply non-abelian Hodge correspondence, you have to apply it not just to the object, but also to the symmetries. In particular, you need to know that the 6 operations are compatible with the non-abelian Hodge correspondence. So there is one ingredient that's missing in the whole yoga, which is that you need to know that the non-abelian Hodge correspondence is compatible with push forwards. Say the ramified non-abelian Hodge correspondence is compatible with push forwards. So you need to prove a theorem that says there is an algebraic way to compute the push forward of a ramified flat bundle, and it's going to give you a ramified Higgs bundle. And you know, if the two inputs correspond to each other with the non-abelian Hodge correspondence, then the two outputs also correspond to each other with the respect to non-abelian Hodge correspondence. So I'll explain this on Friday, but so we worked out this whole program, and we checked that there is a parabolic structure. In fact, there is a unique parabolic structure which is which satisfies the two conditions that you want. One is that the bundle is semi-stable and with vanishing Chern classes, which actually turns out to be extremely stringent condition. There are very few solutions. In fact, there is no obvious way to see that there is a solution until you compute it, and that also it's compatible with the Hecke. So you need to do both, but we did it in this one example, and the geometry is very pretty. So I just want to tell you about it. So in this example, the curve C is going to be an orbifold curve, and it's going to be P1 with 5 orbifold points. 5 Z-mod 2 orbifold points. And n is going to be 2. So we're going to do rank 2 bundles. So this is the first non-trivial example for this whole story. I mean, 4 orbifold points will be an interesting example. Unfortunately, in this case, the moduli space of bundles is one-dimensional. If you do 4 orbifold points, the moduli space of rank 2 bundles on a P1 with 4 orbifold points is one-dimensional. Because it's a genus 0 thing, genus 1 thing. And so you don't really get a serious condition, which is the second chunk class condition being equal to 0. That's a quadratic condition which is hard to analyze. So you could do it with P1 with 4 points, but the problem is much easier, and you don't see all the difficulties in all the stages.
But you have all these symplectic manifolds.
The moduli of bundles is one-dimensional. The symplectic guy is the cotangent bundle. Yeah, but the non-abelian Hodge correspondence for 4 points, the non-abelian Hodge correspondence on both sides will be a non-abelian Hodge correspondence on a curve for 4 points. So the conditions are much easier to check because you only have a first chunk class condition. This is the first case where you get actually a second chunk class condition. Right, so this is the first case where the Euler characteristic is actually negative. It's -1/2. Okay, so this is the example. And so let me say what we really need to do. So, okay, I don't have time to explain that, but the point is that the bundles on this orbifold are the same thing as parabolic bundles on P1 with parabolic structures at the 5 points. So what we want to do is, given parabolic rank 2 Higgs bundle, E phi on C with these 5 points, such that the first chunk class is 0. So this is the guy that corresponds by the non-abelian Hodge correspondence to the local system. We want to construct
Parabolic means a line given at all those powers and compatible with
Say it again?
parabolic means
Yeah, parabolic means, I mean, in the classical description, I'm gonna write everything on Friday, but in the classical description, it just means that at the fibers of all those points, we have given a line, and to each line, to each step of the flux, so between the line and 0 and between the line and the fiber, we have assigned one real number. So there are 2 real numbers in the interval, Huh? Well, half will be, no. The half is the rank. Yeah. So the half is the length of the flux. So if you have a parabolic structure, if you have an orbifold structure with orbifold cyclic group of order S, that corresponds to parabolic structures with flux on anything of rank n, flux where the S.
Yes.
So in this case, we have 2 steps in the flux, so that's these 2. But the parabolic weights are just weights. They're just numbers. So we need to find them because the parabolic chunk class condition depends on them. So I'll write this on Friday. But so let me just finish this in the 1 minute that's left. So we want to construct a C, well, I think I'm going to call it F theta on the stack of rank 2 bundles, parabolic bundles. Again, these are parabolic bundles. On C with these parabolic points. such that, in this case, there is only one interesting Hecke correspondence when you do a modification of a line at each of the parabolic points, such that the Hecke of applied to C to F is equal to F exterior tensor product with E. So there is only one Hecke correspondence in this case because we can only do modification of a line from bund 2 cross C. So this is what we need to do, and we need to do it in a way compatible with all the non-abelian Hodge correspondences. In fact, pullbacks, push forwards, everything. And of course, yeah, so this Hecke condition. So, okay, I'm going to explain this on Friday, but it requires some serious work. So you need really to understand these moduli spaces completely concretely. You need to write the Hecke correspondence with boundary divisors, say what the parabolic structures are on the Hecke correspondence, what the parabolic structures are here and here, and everything. So, Friday.